Hello everyone, welcome to the 24th video of our lecture series. So in this video we are going to solve some problems on Schrödinger equation in spherical coordinate or in 3 dimension. So this is our first problem. So in the problem we have that an electron which is trapped inside an infinite spherical well. So this potential is 0 for r less than a and infinite for r greater than a. So using the radial Schrödinger equation, so what we have derived in our one of our previous lecture video, so you have to determine the bound eigenenergies and the corresponding normalized radial wave function for the case where the orbital angular momentum of the electron is 0. So orbital angular momentum 0 means our azimuthal quantum number is 0 or L is 0. Then we have to show that the lowest energy state for L equal to 7 lies above the second lowest energy state for L equal to 0. And we have to calculate the probability of finding the electron in a sphere of radius a by 2 and then in a spherical shell of thickness a by 2 which is situated between Ra and R equal to 3a by 2. So let us proceed. So let us proceed with our first problem first. So using the radial Schrödinger equation, so let us write down the radial Schrödinger equation. So it is minus h cut square by 2m d2u, and u is a function of n and l both quantum numbers, by r square minus l into l plus 1 by r square, and we have here u n l r which is equal to e u n l r. So it is in which region? It is in region r less than equal to a, where we have our potential to be 0. So and we know that u n l is defined in the following way. So it is r NL R. So we have to calculate when our orbital angular momentum is 0. That means L equal to 0. So orbital angular momentum that is 0. So it represents our L to be 0. So if L is 0, then our equation reduces down to d2u nl r dr square, which is equal to minus kn square un, and L value is 0, so un0 r. So where kn square is 2me by h cut square. So k squared is basically 2me by h cut square. So what is the general solution of this equation? So this is a well-known equation. So its general solution will be plus b sine kn r. So if this is our un no r, then what will be our r? So r n0 r will be u n0 r divided by r. So that means 1 by r a cosine kn r plus b sine kn r. Now we know that r no r, this should be finite at the origin. So what does this imply? So this imply our un0 at origin must be 0. So from here from where we are getting that a must be 0. Also we know that the potential is infinite or aggregate. So we are just applying our boundary condition. So this is our first boundary condition. And what is our second boundary condition? So it is our second boundary condition is potential at r equal to a, it should be infinite. So it is basically kind of rigid wall. So for that we have our radial wave function Rn0 at r equal to a, that must be vanish. So if r at r equal to a, our radial wave function should vanish, then we will get b sin kn a divided by r. So r at r equal to a. So this should be 0. So that imply that our kn a, that must be a multiple integer of pi. So it can be n pi. So where n is 1, 2, 3 and so on. So what is our kn? So kn basically n pi by a. And we know that our kn and energy, they are related, and they are related with the following equation. So 2me by h cut square, that is our kn squared. So En is h cut squared kn squared by 2m. So if we put our value of kn, then we will end up with n square pi square h cut squared by 2m a squared. So this is our energy, and what we have to find, so we have to find the corresponding normalized radial wave function. So we have to find our wave function. That means we have to find out value of b. So how we find the value of b? So that we can find out by normalization of the radial wave function. So from normalization, we are getting r value from 0 to a, Rn0 r this squared, and we have r squared dr, that must be 1. So that will lead to b squared 0 to a 1 by r square sine square knr multiplied with r squared dr, so that should be 1. So this r square and this will cancel out, and we will have b square by kn 0 to, so we are replacing our knr, this is with rho. So if r has limit from 0 to a, then rho has limit from 0 to kna, and dr will be 1 by kn d rho. So we are getting sine square rho d rho. So that should be 1. So if we carry out the integral, we will find this to be, so we can write this as half into 2 sine square theta. Then this 2 sine square theta, that can be written as 0 to kna. 2 sine square theta is 1 minus cosine of 2 theta. So we will get b square by 2 kn, and here we will have rho minus, and in the second term we will have sine 2 rho by 2, and limit is from 0 to kna. So this should be equal to 1. So this will give us b square by 2 kn, and here we will have kna minus sine 2 kna by 2. Now this if we put our value of kn, so that is basically n pi by a. So 2 kna will give us 2 n pi by a into a. So we will end up with 2 pi n, and sin 2 pi n, that will be 0. So this term will boil down to 0, and we are left with b square a by 2, which should be equal to 1. So b is root under 2 by a. So we have find out our value of b. So our normalized radial wave function is thus given. So normalized radial wave function will be r n0 r, which is equal to root under 2 by a 1 by r sine root under 2me by h cut squared r, and e is en. So that is our normalized radial wave function. So we are done with our first part of the problem. So let us proceed to the second part. So we have to show that the lowest energy state for L equal to 7 lies above the second lowest energy state for L equal to 0. So let us proceed. So for L equal to 7, we have E energy on E1 for L equal to 7. So and we know that is greater than equal to V effective for L equal to 7, which is equal to 56 h cut square by 2m square. So it will give us value 28 h cut square by m square. So we know that the second lowest state for L equal to 0 is 3s. So second lowest state for L equal to 0, this is given by the 3s state. So its energy will be for L equal to 0 2 pi square h cut square by m square. Since we have here n value to be 2. So what we are observing? So we are observing that E1 for L equal to 7 is greater than E2 for L equal to 0. So we have the lowest energy state for L equal to 7, it lies above. That means it has greater energy than the second lowest energy state for L equal to 0. So now we have to proceed with third part. So you have to calculate the probability of finding the electron in a sphere of radius a by 2. And we have to also find its probability to find in a spherical shell of thickness a by 2, which is situated from a to 3a by 2. Now we know that the potential is infinite for r greater than a. So for r greater than a, our potential is infinite, and for r less than a, our potential is 0. So that means the probability of finding the electron in the sphere of radius a is equal to 1. Since here we have potential infinite, so electron cannot go there. So that is why the probability of finding the electron is 1 for spherical shell of for sphere of radius 1. So probability like in radial coordinates, so this is suppose r equal to a. So here we have potential 0, and rest all of them we have potential infinite. So electron cannot be any of these places. It is bound to be found in this region. So that is why probability of finding the electron in the spherical shell in the sphere of radius A is equal to 1. So it is obvious that the probability of finding the electron in a sphere of radius a by 2 will be half. So this is so probability will be half. Now we know that since the electron has one maximum probability or total probability 1 to found in this region, so if we have a spherical shell here from r a to r equal to 3a by 2, so in this region we don't have any probability of finding the electron, so it will obviously be 0. So the probability of finding the electron in a spherical shell of radius a by 2 that is situated from r equal to a to r equal to 3a by 2 is 0, because of the infinite potential there is no probability of tunneling at all. Probability of tunneling at all, since the potential has infinite potential has value infinite, so that is why the probability will be 0. Okay, so that is it for the first problem. So we will proceed with the second problem now. So let us now move to the second problem of today's video, and probably last problem of today's video. So we have problem states that the operators associated with the radial component of the momentum PR and the radial coordinate R, they are denoted by PR and R respectively. Okay, so their actions on a radial wave function are given by, so if we act our radial coordinate radial component of momentum, then it will behave like this, and if we act our radial component of the position operator, so it will be behave like this. So you have to find the commutator relation PR R, and we have to find the product of the variance of these two quantities. So these are variance definition, and we have to show that the PR square operator is defined in the following manner. Okay, so let us proceed. So first of all, if we act our position operator on psi r, then it will give us r psi r, and if we act our momentum component, then it will give us minus I h cut 1 by r del del r r psi r. So this will give us minus I h cut 1 by r psi r minus I h cut del psi del r. So this is our PR, and what will be the value of this PR r psi? So PR r psi r will be minus I h cut 1 by r del del r, and r psi r is basically, this will give us this quantity. So here we will have r square, so r square psi r. So what will be the value? So it will be I h cut 1 by r multiplied with 2r psi r, and we have 1 I h cut 1 by r square del psi del r. So it will have give us minus 2 I h cut psi r minus I h cut r del psi r del r. So what will be the action of the commutator on a function? So let us proceed. We have to find this PR r. So PR r on a function psi r. So it will give us PR is minus I h cut 1 by r del r, and r have we as r. So it will give us minus I h cut 1 by r del r square psi r, and plus I h cut del r psi r. So it will, this value we have already evaluated. It is minus 2 I h cut psi r minus I h cut r del psi del r, and this will give us I h cut psi r plus I h cut psi del psi r del r. So this term and this will cancel out, and we will end up with minus I h cut psi r. So we are operating this commutator on psi r, and we are getting this value and psi r. So this commutator PR r, it has value minus I h cut. So the commutator relation we have find. So now we have to find our del P r, where we know that this r, this is defined as r squared minus r value squared, and PR we know is defined as PR will be defined as PR squared minus PR squared. So using the, so we know what is our, so we have to find out this. So we know that the generalized uncertainty principle for a pair of operator A and B. So if we have two operator A and B, then from generalized uncertainty principle we know that delta A delta B, it must be greater than equal to half, and we have here expectation value of A B commutator. So this is our generalized uncertainty principle. So if we represent our A by PR and B by R, then we will get delta PR delta R will be equal to greater than equal to half expectation value of PR and R. So this is greater than equal to, and this we have found out already. So this is minus I h cut, so it will be greater than equal to h cut by 2. So we are done with our first part of the problem. So let us now move to the second part. So we have to show that PR squared operator is same like this. So for that, what we have to do? We have to operate PR on psi twice. So what is our first time? So if we apply PR on psi, what is we are getting? So let us copy that. So we have to find the representation of PR square. So PR square psi r will give us PR acting on PR psi r. Now this PR psi r is already known, so this is minus I h cut 1 by r psi minus I h cut del psi del r. So what is so now what we will get? So if we write down PR, we will get minus I h cut 1 by r del r, and here we will have r, and in place of psi r we have to write down this. So it will be minus I h cut 1 by r psi r minus I h cut del psi del r. So we will get, so we can take out this minus I h cut common. So we will have minus I h cut squared 1 by r del r, and here we are getting psi r plus r del psi del r. So what we will get? So this will give us minus h cut squared, and here we have 1 by r. So first term will give us del psi del r, and from the second term we will get del psi del r plus r del to psi del r square. So so what we will get? So if we do this carefully, so we will get minus h cut squared 1 by r 2 del psi del r plus r del to psi del r square. So this is one form, but it seems that this is not adequate with our required form. So let us do one thing. So what we will do? So PR square psi r. So we will write down our first PR square as h cut square 1 by r ddr, and here we will have r 1 by r ddr r psi. So if we have this, then we will have h cut square 1 by r del 2 del r square r del psi del r. So that means our piece r square that has the functional form as h cut square 1 by r del 2 del r square r. Okay, so we are done with our problem. So that is it for today's lecture video. So we will so the next lecture video will be our last video. So in that video I will discuss some more problem regarding various topics, some 2-3 problems or so, and then we will wrap up with this series. So and like if and in like future I will try to make like this problem solving series on various topic, like from classical mechanics, electrodynamics, and so on. Okay, so we will meet on our next lecture video.